All right, so here's our review of section 1.1, just a review of functions. So let's just remember a function. So I'm going to just write out a little definition here. A function, what's called f, is a rule that assigns each value of x, which is an element in the domain, to exactly one value, it's called y, which is an element of the range. All right. So in other words, for every x that you substitute into, let's call this a function calculator. Okay, we'll call this little function calculator. For every x value that you substitute into this calculator, you will get exactly one y value as an output. And let's also recall that, the inputs, so I'm going to come over here to the left, the inputs are also considered to be independent values. The outputs are also called the dependent value also. And if my handwriting is not that great, just email me, let me know, and I will slow down a little bit. Okay? Now, the thing that we're really concerned with here is that within functional notation, so let me give you an example here. So f of x equals, we'll say x to the second plus 1. This is called the argument. I've also, let me spell that right. Sorry. I've also reheard this. It doesn't sound right. I also heard this referred to as a relation, meaning that this part of the function here will relate the x variable and the y variable together. Okay? So, real quick on the left-hand side, just remember the x represents the input or your independent variable or value, and that is what we evaluate the function at. So if we say given f of x equals x squared plus 1, if I want you to find f of 3, what I'm really asking you to do is just take the value 3, substitute it into your function, and then evaluate it. So 3 squared is 9, 9 plus 1 is 10. And what we found is that when x equals 3, or the input equals 3, the output equals 10. And there are multiple ways that you can think about this. Like I said, I like to think about this sometimes, especially if I'm teaching this in like an algebra course. I think about it as just like a calculator, where this calculator's name is f of x. The only thing that this calculator knows how to do is x squared plus 1. That's it. So whatever you type into the calculator, let's say it's a plus h. We type that into the calculator. When you hit the enter button, initially, it is going to spit out a plus h quantity squared plus 1, because the a plus h will get substituted in for the variable, and then it just evaluates it. Now, hopefully you can see this and know that the simplified version of this is going to be x squared plus 2ah plus h squared plus 1, and that would be the final output. Okay, so that's how we evaluate functions. We define what a function is. The next thing I want to go over here is just identifying when does a function actually exist. So one of the ways that we can identify functions is by the vertical line test. So the vertical line test is actually very simple, okay? Basically what it is that when you go ahead and you have a function graph, so let's say we have a circle here, okay? And what I'm asking you is this graph a function? You would use the vertical line test. And the idea behind it is every vertical line that passes, you know what? Let's use the word intersect. Every vertical line that intersects the graph only once is a function. So as you can see here with the circle that I drew, if I just change the color here real quick and I were to draw a vertical line, notice that I hit twice. Therefore, this is not a function. Sorry, it's been a long time since I've wrote on my laptop here. So I'm getting used to writing with the pen again, okay? So the vertical line test gives us a very fast and efficient way to determine if we have a function or not. Let me give you one that is a function real fast, okay? So we might have something that looks like this. All right, let me exaggerate this a little bit here. So you know it keeps going on and on to the right and then to the left. No matter where I draw a vertical line here, notice that I only intersect this graph once. Therefore, this is a function. So I'm just going to write the word function, put a big happy face because I'm very excited because now I know I have a function, and functions allow me to predict things because I know for every input there's exactly one output. So I can start to predict things. So now that we've identified what a function is, we reviewed the vertical line test. I kind of used some words earlier, and now I really want to define them. So domain and range. So when you're thinking of domain, I think the easiest way to think about this is to think about x values. In other words, if I'm going to use that function, what x values am I allowed to use? And then the range, well, those are going to be your y values. They're going to be the outputs. So as long as you have a function, these two go hand in hand with each other. All right? Now, sometimes students have a problem with finding domains. See, finding domains on a graph is actually very simple. So like, for example, here, let me just go ahead and draw like a little graph real fast. We'll put this here. We'll have it come down, and then we'll have it come to right here. And that is an open dot. Okay? So we'll do this. We'll put that at 1, and we'll put this at -1. All right. So now we're looking pretty good. So my domain for this graph, remember, is going to be x values. In other words, how far to the left, how far to the right. And we always write them in interval notation. Okay? So for us, our domain is going to be bracket 2, comma, 2 with a parenthesis. Now, I did this on purpose. First, that is a closed dot, which means I'm allowed to include that point, both x and y values for that specific point. Remember, all points have an x component and a y component. Now, on the right-hand side, on the far right, that's the largest x value I'm going to have. But notice since it's an open dot, I cannot include that x value. I'm going to get infinitely closer to 2, but I'm never going to actually reach 2. So that's why our domain here is going to be -2 inclusively, all the way up to 2 exclusively. My range, all right, they're going to be the y values. So in other words, it's like how high does this graph get and how low does this graph get? So as you can see right here, that's the value -1, y equals -1, and that's going to be the lowest value. It's going to be the smallest value. And since my graph, and you're going to hear this a lot, is smooth and it has like a continuous curve, I can include that. And then the largest x value, or I'm sorry, the largest y value I get is actually right back in here again. That's as high as the graph gets. So it's going to be +1. And since that is a solid dot, I can write a bracket. So finding domain and ranges, pretty easy when you are looking at a graph, okay? It's a little bit different though when you were trying to figure out the domain and range for just, let's say, a function where there is no graph. So like, for example, let's find a domain for the following. Okay, so let's see, part A, f of x equals x squared minus x minus 6. We'll do this one. I'm going to do a couple of them, all right? The best approach, all right, when we're just finding a domain, I'm not too concerned with the range right now. I'm really concerned with domain. Because, you know, if you're going to buy this expensive calculator that can only do one function, you better make sure that you're putting in numbers at work so you're getting values or outputs that you can write down, all right? So the easiest way for me to kind of go about this is to give you a technique. I'm a huge fan of techniques. One of the things I love to do in my free time is cook. I love cooking, and I like following recipes. I treat cooking as if it were a science. So that's the way I since I look at cooking that way, it's because of my mathematical background. So the first thing I always want to do is I just want to try to identify the type of function. That's my first step. Okay? So with this, I have a polynomial. Now, as far as I'm concerned, I can stop right here. And that's because I understand that the domain for all polynomials, and this is huge. So if you don't know this, you definitely want to write this down because I'm going to put like a little star next to it. So the domain of all polynomials is negative infinity to positive infinity. Or another way you could just say that would be all real numbers. All right? In other words, it doesn't matter what x value I choose, I'm always going to get an output value. An easy way to kind of look at that would be to go ahead and graph this. So I'm going to open up Firefox right here. I'm a huge fan of Firefox. So if you're not using Firefox, I would highly recommend it. Even for you Mac users, Macs are they're really good computers, but they just don't play nice with anything else other than Mac products. So I'm just going to go to Desmos here. Now, Desmos is a free graphing calculator. If you have a graphing calculator like a TI-83 or 84 or whatever, that's great. But if you don't sweat it because you can always use Desmos. It's free. And give me a second here because I hate the way they have this, the minor grid lines. I don't even want the grid. I just want a nice blank canvas here. And I'm just going to go ahead and type in our function. So my output equals, and I think I used x squared minus x minus 6. And as you can see here, there's my vertex all the way down at the bottom. I can go ahead and just click on that. But remember, I'm concerned with domain here. I want to know if I choose an x value, will I still get exactly one output? And if I just zoom out here, so I just zoom out and keep scrolling up, you could see on the very bottom of the screen above the toolbar, in gray are still my x values. But as you can see here, I'm always going to get exactly one output. So no matter what I do, all polynomials will always have a domain from negative infinity to positive infinity. The question becomes, all right, what if I don't have something like that? And that's going to be in part B. So we're going to extend our steps here. So step 1, identify the type of function. The first example was a polynomial. I didn't need anything else. But the second example here, p of x equals 2x plus 3 all over 3x plus 1. All right, so for me, step 1, identify the function. Well, this is a rational function. It's a ratio of a numerator and denominator. I mean, if we're really being honest here and trying to just speak simply like if we were in a grocery store and not in an official math presentation, I would just say it's just a fraction. It really is. All it is just a fraction. And the one thing that I know, and this is step 2, is once you identify the type of function, you need to ask yourself, are there any restrictions? Okay, that's going to be step 2. And the answer to this question is, well, since you have a rational expression or a rational function, the answer is absolutely. The restrictions for fractions are our denominator cannot equal 0. All right? So step 3 then is going to be find the restrictions. Okay? So if you think about that, I'm going to do exactly what I just wrote. I'm going to take my denominator, 3x plus 1. And I know this is going to sound weird at first, but I'm going to set it not equal to 0, and then I'm just going to solve for x. And by doing that, subtracting 1 from both sides, 3x equals negative, or 3x does not equal negative 1. Divide both sides by 3. What I just found is my restriction. In other words, I can use any x value I want into this rational expression. However, I cannot use negative 1/3. That's going to break my domain. And that's going to be step 4, which is just stating the domain. And I'm going to do this 2 ways. Because some people learn different ways, so I'm going to give it to you 2 ways. The first way you can write the domain, simply state it. All real numbers, comma, x cannot equal 1/3. That's the first way you can state the domain. The second way is interval notation. Now, I'm going to show you what this looks like using a number line. All right? Right in the middle of this number line, I'm just going to write negative 1/3. And here's the key. We know we cannot have negative 1/3 in our domain. So I'm going to put a big circle right there. I also know that I can use any number before negative 1/3. So I can go ahead and shade this side. And I can use any number after negative 1/3. So I can go ahead and shade this line. So this is going to be the union between negative infinity and negative 1/3 exclusively, because I cannot include the negative 1/3, or negative 1/3 to positive infinity. And that's the second way that we can go ahead and write our domain for this problem. Okay? So I'm going to give you one more example here, because I think it's always pretty good to show this. All right? So the next example that I want to do, let's see. I'm going to use j of x, because my first name starts with a j. And this is going to be the square root of 4 minus x squared. Okay? So, step 1 again. Now, I'm not going to write the steps. You can go ahead and scroll up to get the steps if you wanted to. This is a video, so you can pause it and go back and hit rewind, which is fantastic. Step 1, identify the type of function. It's a radical. Step 2, are there restrictions? Yes, the radican has to be greater than or equal to 0. It must be positive. So, to find my restrictions, I'm going to take the radican, which is 4 minus x squared is greater than or equal to 0, and I'm going to solve for x. See, a long time ago, in a galaxy far, far away, there's your first Star Wars reference of the semester, you were taught all of these different words, like radican, and divisor, and dividend, and unfortunately, us math people, we do expect you to know what they mean. So your best bet is if you read something in your book, or if you see something and you don't know what that word represents, try to look it up. If not, just email me, give me an idea of or the sentence of where it occurred in, and what I can do is I can write you back something, or I can make a video or something like that. Not a big deal. So we're gonna go ahead and we're gonna solve this. So what I'm going to do is I'm going to add x squared to both sides. Okay? Now, this is only personal preference here. It's just the way I do things. I don't like the number first and the variable second. It's just the way I am. So before I do any math, all I'm going to do is just switch them. X squared is less than negative, or I'm sorry, x squared is less than or equal to 4. It's just me. Now, the easiest way to solve this is just to take the square root of both sides. Or another way to think about this is the double inequality where x is bounded in between -2 and 2. So what I know here is my domain, and I'm just going to state this the way it looks right now. My domain is going to be -2 less than or equal to x, which is less than or equal to 2. Another way to do this is interval notation. Okay? And if you are really savvy and you recognize the type of function that we have, this is actually just the top half. Boy, it'd be nice if I could spell correctly. Top half of a circle. That's all it is, with radius equal to 2. So 1, 2, 1, 2, 1, 2. You're going to have to forgive my artistic abilities. And these are solid dots, by the way, because you can include the endpoints. All right. Like I said, you're going to have to excuse my artistic ability. I went to school for mathematics, not for art. So I am not a good artist. But anyways, so let's see here, because we definitely did a bunch so far. And I just want to recap what we did. So I'm going to scroll all the way up because we're gonna kind of change gears a little bit. So first, we defined what a function is. We think about it as a calculator where we have inputs and outputs, or independent values and dependent values. We learned about the argument relation, which is, I guess, the function itself. We learned how to evaluate functions. Be really careful, especially with a situation like this. A lot of students, when they see the quantity of a plus h squared plus 1, for some reason, they're going to write a squared plus h squared plus 1, and that is definitely incorrect. So please don't make that mistake. Then we looked at ways that we can actually find whether or not something is a function if we are given the graph, and that's using the vertical line test. Very simple. Lastly, we looked at what domain actually is, and we think about them as x values. Range are going to be the y values. Given a graph, can you calculate or can you find the domain and range in interval notation? We did that. And then lastly, which is, I think, the most important, finding domain of algebraic expressions and understanding the type of functions you are given. I'm almost positive, and I could be wrong, so just take this with a grain of salt. But in pre-calculus, you would have learned family of functions, like a linear function, a quadratic function, a cubic function, an absolute value function, a square root function, and so forth. All those parent functions have domain and ranges that we were supposed to learn. So if you don't remember what they are, all you got to do is just ask me. I can post something for us. Not a big deal. But the reason why I'm really emphasizing them is that they help us to do, and I'm going to look at, which one do I want to look at? I'm going to look at part B here. They help us with these steps right here, which are step 1, identifying the function. Step 2, asking yourself, are there any restrictions about that function? For example, if you have a fraction or a rational expression, a rational function, you know denominator can't be 0. If you have a radical, like the square root, you know it has to be greater than or equal to 0, and so forth. So you always want to make sure that you have those in your back pocket so you can pull them out whenever you need it. Now we're going to talk about compositional functions, or a function within a function. So composite functions. All right. So real quick, functions are called linear operators, meaning that you can add functions together. So if you have, let's say, f and g, you can add them together. You can subtract functions. You can multiply functions. You can even divide functions, provided that g does not equal 0. Composite functions are when you have a function inside of another function. So let me go ahead and define what that is. So definition, I'm going to call this composite functions, or just a composite function. And here's our definition right here. Given two functions, let's call them f and g, and that's very standard. In every textbook you see f and g. The composite function, sometimes referred to as compositional function. Now this is really important the way I'm going to write this, so make sure you're paying attention. F open dot g. We read that as f composite g. Is defined by f composite g of x is equivalent to f of g of x. Okay? Now, the way that we think about this is we want to evaluate the inside function first. And then using that result, we evaluate the outside function, which in this case happens to be f. So, mathematically, it is evaluated, and I'm writing this in a very specific reason. You'll see why when we get into the chain rule. So it is evaluated in two steps. All right, and what I'm going to do is I'm going to show you visually how this is evaluated. So here's x. Here is our, oh, that's a horrible looking rectangle. All right, so here's x. Here's our calculator. This is our function calculator. In this case, we're going to call it function g because that is the inside function. And whenever we hit enter on the calculator, it's going to give us some value of g of x that we're going to let u equal. Now, this expression is going into our second calculator. This is called function f, okay? And it's going to output another function, which had a little bit more space here. But this is the power of technology. I can just move over. And this output is going to be, and I don't mean this as a joke, it's going to be f of u. And I'm going to abbreviate that as like the letter y, okay? And that maps all the way back to f of g of x. All right? So in other words, and I think a really easy way to think about this here is you evaluate the inside function, and then whatever that value is, you substitute it into the second function. And that's it. That's all you got to do. Okay? I hope that makes sense. All right? So let's go ahead and let's actually evaluate a function or a compositional function. So if f of x equals, we'll do something simple, x minus x squared, and g of x equals x plus 1, find f of g of 2. All right? So remember, and I'm going to draw this out first, and then the next example, I'm just going to use algebra to do it. So we have two functions here. The first one is called g, because that's the inside function. And then the second one is called f, that's the outside function. G only knows how to do one thing. It knows how to take a value and add 1 to it. F also knows how to do only one thing. And that's going to be, it takes the input and it's going to find the difference of the input minus the input squared. That's it. So for us, our input is going to be 2. So when we turn on the function machine or the calculator, the 2 goes down into the first machine, the first calculator. 2 plus 1 is 3. And then it goes right into the outside function or the f function. And it'll substitute a 3 in for each variable. We know we need to evaluate the exponent first. So we're going to get 3 minus 9. And 3 minus 9 is negative 6. So f of g of 2 equals negative 6. That's exactly how compositional functions work. Okay?